first one, right? When s equal to, so when you plug in 0, okay, you're actually going to see that here, you can see the 0 here, okay? Now, what I'm trying to say in essence is this. If I plug in 0, okay, if you take a look at what I have here, okay, I'm actually plugging in 0. But if I want to write this, it's going to be what this guy mean is x raised to power 0, probability of x equal to 0, okay, plus, right, s raised to power 1, okay, the probability of x equal to 1. Can you see that? Okay. Now I will continue to go all the way to infinity. You can see that guy. Now, if I now have this guy now and I plug in s to be 0, if I plug in s to be 0 in all of this, of course I'm going to get 0 at the end of the day. So that was why. And if I got 0, okay, if I got 0 at the end of the day, for g of s equal to 0, it is the same as the probability of x equal to 0. This is by law. G of s of 0 mean the probability of s equal to 0. What does that mean? What is the implication? If they want you to find the probability of s equal to 0 from a distribution, if you derive the probability generating function for that distribution, just plug in 0 wherever you see s. That will automatically give you the probability of x equal to 0. I told you the essence of probability generating function is actually for probabilistic computation. Now, I want to move right now. Please pay attention. Okay, pay attention. I actually want to move right now. Okay, pay attention. Okay, now, that is the first property. I'm going to go to the next. You know, what did I do the other time? I plug in 0. When I plug in 0, it gives me probability of s equal to 0. What if I plug in 1? Plugging in 1, I plug in 1. When I plug in 1, it's going to give me 1. How? How is it going to give me 1 when I plug in 1? Okay. Now, this is the formula. You take a look at this. What are we doing? Okay. This is summation x raised to power x, the probability of x equal to this. Okay. And where s start from 0 to infinity. You know, this is the formula g of x, right? Now, when I plug in 1, okay, that's what you're saying here. Plug in 1. When I plug in 1, oh my God, what is the sum of probability? Sum of probability is 1. Exactly. That's why you have this. Can you see that? So when you derive probability generating function from any discrete probability distribution and you plug in 1 to what you're generating with respect to, if you plug in 1, it should give you 1. That is how to check if your probability generating function you derive is correct. You remember when we're dealing with the moment generating function, what do you think we're plugging in? We're plugging in 0. When we plug in 0, it should give us 1. Right now, in the probability generating function, plugging in 1 should give us 1. Now, because of that, you can see now. Now, this is what I now quickly want to do. Please pay attention. And I want to visit. So this is for you to check whether your PGF, the probability generating function you derive, is correct. If your probability generating function you derive from a distribution is correct, when you plug in 0, it should be equal to probability of S equal to 0. When you plug in 1, then it should give you 1. Okay, now let us now go to the binomial. You know what I want us to do now? I want us to derive the probability generating function for binomial and after getting for binomial, then we're now going to check the property. We check for 0, we check for 1. Okay, please pay attention. Let me quickly do this. I think I want to check if this is going to work. Just 1 second. Otherwise, I'm going to make use of the board. Okay, so let me see. I want to see if I can do something here. Now I see loading. You know if it's going to connect. If it doesn't, now we'll make use of the board. Oh, not connected. Okay, I can see. If I have you, just 1 second. Because if I'm able to use an iPad will be so fast compared to. Okay, it's just rolling, doesn't connect. Now, oh, 1 second. Okay, now I'm gonna do something now. I want to walk you through this. Okay, please pay attention. I want to walk you through that. Now, we have. So? No, I just want to connect my iPad, but it's just it's network. You know, I want to see if I can, but it said it's connected. Okay. I connect to that, and I want to. You can see to Zoom, but it's not really working. So that's okay. I'm gonna use the board. Okay, so I have binomial distribution. Okay, with parameter days, and the probability of x in binomial is n combination s, p raised to power s, q raised to power n minus s, start from 0, 1, 2, all the way to n. Now, I want to generate probability generating function, which is going to be expectation of xx, which is going to be summation s start from 0 to n for binomial case, this, the probability of that. Okay, now if you take a look at what I have right now, so the g of s is now going to be summation s start from that to that, s of s, then the binomial, and combination s, p raised to power s, q raised to power n minus x. Okay? I need to take a look at what I have right now. Okay? Now, when you take a look at this, okay, I can rewrite this as summation and combination s, this and this. PS raised to power x, Q raised to power n minus x. Then S start from 0 to n. Look at that. Okay? I'm actually going to have that. Now, if I have this guy now, I have to recall from binomial theorem. Okay, from binomial theorem. Okay, recall from binomial theorem. Okay, if I have a plus b raised to power n in binomial theorem, is summation s start from 0 to n. Okay, n combination s, a raised to power s, b raised to power n minus x. This is recalling this from mathematics. I want to compare this guy with this guy. I want to compare that with that guy. I have this one, I have that one. Then my A is going to be PS, right? And B is going to be Q. So if you compare that with that, okay, okay, A is going to be what? PS. B is going to be Q. And we're told that when you have something like this, it is A plus B raised to power n. So because of that, I'm actually going to say G of S is using A plus B raised to power n. I'm actually going to have PS plus Q, okay, raised to power n. Okay? I'm actually going to have that. Okay? Now, I need you to pay attention to what we're doing right now. This is the moment generating function. Okay? This guy is the moment generating function of a binomial distribution. Oh, sorry. That's a probability generating function of a binomial distribution. Probability generating function. Now, we will now want to investigate the property of a PGF. Okay, you know, if we want to check whether the property of a PGF actually holds. So we want to check whether the property of a PGF holds. Don't forget, the other time in the property, what did they tell us? We're told that G of 0 is the same thing as this, right? That is number one. Number two, G of 1 equal to 1. Okay, these are properties, okay, of PGF. Properties of it. Now, let us now investigate for that. Whenever you derive the probability generating function from a particular discrete distribution, you need to investigate this to see whether your expression for PGF is correct. Now, let us investigate for that. For binomial now, let's plug in S to be equal to 0. Okay, S to be 0. This is going to be P of 0 plus Q raised to power n. What do I have here? Q raised to power n. Right? Okay. Now, if you take a look at this 0, I got Q raised to power n. Now, does this equal to the probability? What is the probability of S equal to 0 in binomial? Don't forget, you know, S equal to 0 is actually Q. You remember? Failure. You know, if I want to consider one Bernoulli process, you know, for one if this is for binomial, automatically for Bernoulli, it's going to be this, right? There's not going to be raised to, because n is going to be 1, right? If I plug in 0, what am I going to have here? Q. What is Q? That is probability of failure, which is probability of S equal to 0. Because in Bernoulli, when S equal to 0, that's failure. Okay? When S equal to 1, that's success. Okay? A failure comes with probability Q. and success come with probability P. Now, this is verified. Okay? But what of, can we verify this to see whether when I plug in 1, it's going to be 1, okay, into that. Okay, so the G of X1, okay, P1 plus Q raised to power N, which is going to be P plus Q raised to power N. Don't forget, P is the probability of success, and this is probability of failure. Success and failure are mutually exclusive. They should be complementary the other. So this should be 1. So 1 raised to power N. What is 1 raised to power N? That's going to be 1. We just proved that. So for that distribution, and which is exactly, that is what we're doing here. Please pay attention. Now, you see this? We derive, okay, this is the PGF, and we verify the property. Can you see the two? We verify the property. Okay? We just verify the property right now. Is there any question here on how we verify this property? Any question on that? Then we're going to move. If there is no question, I'm actually going to move right now. Now, I want to go into Poisson distribution. I also want to derive the probability generating function of Poisson. Okay? When I do that for Poisson, I will do that for geometric. Okay? Then before generalizing. So let's start with the Poisson now. Let's start with the Poisson distribution. Now, I think I'm going to quickly explain the one for Poisson here. It's kind of easy. Okay? Now, what actually happened is that here, okay, if I want to write a formula for probability generating function, okay, the formula, don't forget, is going to be summation, okay, S start from 0, because for Poisson, it's going to be S start from 0 to infinity, okay, then don't forget the X raised to power X, of course, then the probability, that particular probability distribution you're talking about, okay, the probability distribution that we're talking about, okay, this guy here is Poisson. Can you see that? Okay, if I plug that in, I'm going to have this guy. Can you see what I have right now? Okay, I'm plugging in the probability distribution for Poisson. This is what I have. Now, you know what I'm going to do? Okay, you know, we are here now. Give me 1 second. Pay attention. Okay, we are here now. Okay, can you see? I can simplify. You know, this guy is raised to power S. Lambda also raised to power S. I can bring the two of them together and they're going to carry X. Can you see that? Mathematically, bringing them. Then the one that is independent of S, constant, this guy is going to come out. That's why I say that guy coming out. Okay? Then we have this. Now, oh my God. You remember what we did the other time. There's a particular rule. Take a look at this. Whenever I'm summing S start from 0 to infinity, something raised to power S divided by S factorial is always going to be exponential raised to power, that's exponential raised to power this guy here. That's why you see this. That's from mathematical law. Okay? The mathematical law that says that summation S start from 0 to infinity A raised to power S over X factorial, okay, is the same as exponential raised to power A. That is what we're using here to come up with this. Now that you have this one, you just need to simplify this. Simplify that will give you that. That is the probability generating function of a Poisson distribution. Now, if you have that guy as a probability for generating function for a Poisson distribution, you can investigate for property. Okay, you can investigate G of S, you know, where S equal to 0 and where S equal to 1, want to do that right now, please pay attention. Okay, I needed to pay attention. Okay, now we want to investigate that now. Okay, let me see. Okay, now here, plug in, let's investigate, plug in S to be 0. Okay, plug in S to be 0. Okay, when you plug in S to be 0 here, this is going to give you exponential, let me see, raised to power negative lambda. Okay, this is going to give you exponential raised to power negative lambda. So this exponential raised to power negative, because when you plug in 0 here, okay, you're actually going to have that. This is the same thing as probability of S equal to 0 in Poisson. Do you want to confirm? Oh my God. I'm going to confirm right now. Take a look at this. I want to confirm from here. If this is Poisson, plug in S to be 0. What do you have? Plug in S to be 0. Lambda raised to power 0, 1. Is 0 factorial 1. What do you have? Exponential raised to power minus lambda, which is what we get here. That is the probability of S equal to 0. You can see that now? Now, the next thing that you're going to do, you investigate is the G of, is this guy, is the G of X. When you plug in S to be 1, does it give 1? Okay, here, plug in S to be 1. Oh my God. When you plug in S to be 1, I'm actually going to have 1 minus 1, right? Which is going to be exponential lambda, okay, 0, which is going to be exponential raised to power 0. What is anything raised to power 0? 1. Verified. You know, you do statistics with confidence. The moment you know the properties, assuming I gave you a probability distribution, I asked you to derive the probability generating function. Of course, you can check whether your expression that you got is correct. Okay, I'm actually going to move right now. I want to move to, geometrical distribution. I want to move to geometric distribution now. Now, say geometric. Okay, if you are given, it's the same procedure. You're given geometric with this as a probability mass function, and this is the state space. Okay, now you want to figure out the probability generating function. Of course, you're using the formula because this guy here is the probability of S equal to S. Okay, and if you take a look at where you are here, okay, if you take a look at where you are here, S is raised to power X, Q is raised to power X. I can combine them together and bring this P out because it's a constant. That's why P is here. They combine this and that. Then we have this guy, right? When I have that guy, oh my God. When I have that guy now, I'm actually going to apply, this is looking like a geometric series, okay? I've taken a look at what I have in the parentheses, okay? QX raised to power 0 plus QS raised to power 1, okay, plus QS raised to power 2, and there we go all the way to infinity. When you take a look at what I have here, this is like some sum of a geometric series, okay? And what is the sum to infinity in geometric series? Don't forget, sum to infinity in geometric series is first term divided by 1 minus common ratio. You've done this in high school. What is your first time? It is this guy, 1. This guy is the first time. what is the common ratio? Is QS. And that is why. See that? So here, this way here now, when you apply this, this is going to give you 1 over 1 minus QS. Okay? That is what you're going to have from this guy. Don't forget, there's a P here, right? Then you multiplied this guy by P. That was why you get this. That is the probability generating function for geometrical distribution. Okay, you can investigate again. Can we investigate when s equal to 1? When s equal to 1, this should give us 1. We're going to see now. Let's play a game. Okay, let's play a game now. Let's plug in 1 into the expression to see whether we're going to get 1. Okay, we want to plug in 1 into the expression. Okay, into what you got. Into this guy. Wherever you see s, plug in 1. What are you going to have? P over 1 minus Q. What is 1 minus Q? P. P divided by P, 1. That's correct. And don't forget the domain, because this guy is only defined, okay? This guy is only defined when, when the absolute value of QS is less than 1. Because situation where QS, who can tell me what is going to happen? When the entire QS equal to 1. What is going to happen here? When QS equal to 1, yeah? Eh? Like when QS equal to 1, what's going to happen to that fraction? Over 0, and something over 0 in math. That's undefined. Good job. Send me a message for extra credit. That will be undefined. And that was why we said the absolute value of QS must be less than 1, and the absolute value of S must be less than 1 over Q. Okay? That's what I mean. Super cool. Okay? Now, I wanted to take a look at that. Now, let's continue now. Now, if I have the GS, the probability generating function, which is defined as this, okay, which we are defined as this guy, where the PS here is the PMF of a particular discrete distribution, I can rewrite it as this in a very listing form, okay? And I told you, okay, when we plug in 0 for S in the probability generating function, that will give us the probability of S equal to 0. Now, let me tell you this. Can we have a way to derive the mean and variance from any given probability generating function? Yes, just like what we did in the moment generating function. Okay, if I have this guy now, please pay attention. If I have this as the moment generating function, and I differentiate with respect to S, I'm going to have that. And after differentiating, okay, and I plug in my S to be 0, okay, when you plug in S to be 0 here, 0 here, 0 in the S, what are you going to have? P1. That P1 is the probability of S equal to 1. You remember the other time? The probability of S equal to 0 is when you plug in is 0 for S in the probability generating function. But how am I going to get probability of S equal to 1? Then I have to differentiate the probability generating function before I set S to 0. So